Hello everyone. As I'm sure you know from your grades, Lab 3 was a disaster. When a class does uniformly badly on an assignment, it is not a sign that the class is a bunch of flunkies. In fact, it appears in your case that the opposite is true. Your performance on all other elements of the course has been outstanding. Such broad failure usually means that the assignment was flawed. In Lab 3, we are probably asking too much of beginning students. First, you must design the experiment. You select the ball, the rolling distance, the ball speed, the height, the distance and time measurement methods. It works if you make good choices, and it doesn't if you don't. Yet we did not teach any principles of good experimental design, and it's asking a lot to ask of beginners to know how to design experiments in order to obtain precision and accuracy. Secondly, you need to know some Excel data analysis methods that some of you know, but are generally not familiar to most. And so as a consequence, there were really only 2 good grades in the entire class on this lab. So I'm going to do this lab with you in this presentation. Try to teach some methods and ideas about how you go about designing measurement techniques in labs. For some reason that I'll never understand, science education seems to place the bear of teaching experiment design on the physics department. So these principles are actually useful in all areas of science. And they ultimately get down to the question, when you measure something, why do you have faith that it's correct? As I'm sure you remember, the lab instructions describe an experiment where we build a ramp on a table or a countertop. We start the ball at a mark on the ramp so that it rolls down the ramp and across the countertop. It flies off the edge and hits the floor some distance from the point immediately below the edge of the countertop. You can see my picture of my setup here. I have an advantage over you guys. Mine's going to work better because my ramp's held up by a physics book. We begin by making 2 marks on the countertop that are a distance d apart. Using a timer such as a cell phone app, you measure the time for the ball to roll from the start to the stop. And then the ball speed will be the distance between the start and stop divided by the time. The fundamental question when we complete an experiment is, do we believe the results? And so when you begin an experiment, you should begin by asking yourself the questions, what can go wrong? And where in all of these measurements are the sources of error? And then we design to eliminate error so that the final answer is as precise as it can possibly be, meaning that it has the least amount of random error, and as accurate as it can possibly be, meaning that we have convinced ourselves that we've eliminated all systematic errors. So in this experiment, the first thing that we're going to do is measure the velocity of the ball as it rolls across the table so that we know what it is when it flies out into the air. And we do this by rolling it between 2 points on the table and measuring its time. The ball itself is probably the first thing that we should investigate. If the ball has a very large diameter, then we are not really very sure when it crosses the start line or when it crosses the stop line. If we're trying to judge the front edge of the ball or the back edge of the ball or the center of the ball as it goes across those. And so we have a potential error that's, of the order of the diameter of the ball. You can probably guess better than that, but nonetheless, the bigger the ball diameter, the more uncertainty we're going to have in the when to push the start button and when to push the stop button on the timer, which will become an error in the time. It will also give us a big uncertainty on where it actually hits the floor. So in general, a small diameter is good, a big diameter not so good. If the ball rolls differently each time that we run a trial, we're going to get a lot of variation in the results. So you want a ball that has a smooth, hard surface. One that will roll nice and smoothly, not wobble as it rolls, not bounce over features on the ball as it rolls, and not lose a lot of energy to friction due to the roughness of the ball. We don't want this ball slowing down as it's proceeding. Finally, a dense ball will be best because it will have minimum air resistance as the ball flies. A ping pong ball might satisfy the nice and round and smooth and hard surface, not very big diameter, but a ping pong ball will probably have a fair amount of air resistance and not fly very well. You can see in the picture below two example balls. The good ball is a glass marble. It's the one that I'm going to roll in this experiment. I found it literally out in the yard and working in the garden one day. The bad ball is one of those balls you throw in a dryer when you're trying to dry a comforter. Believe it or not, one of you actually used one of these. And there were other balls that were comparable. Now that we've selected a ball, we need to look at the issues regarding the velocity measurement. If we measure the time with a cell phone app stopwatch, we will have uncertainty in deciding when the ball is crossing the line, and then we will have reaction time variation. The combination of these errors at the start and the stop crossing is probably about a tenth of a second. If we want that tenth of a second to be a 10% error in our time measurement, then we will be looking for a total time of about 1 second. And if we're willing to accept a 20% error, then the time will be about a half a second. Time is the distance divided by the speed. So if we work with high speed, we will need a long distance between the start and the stop points. We'll also be making a range measurement, and we'll want to manage its error. There will be uncertainty in the eyeball landing point, and there will be some uncertainty in the 0 point as well. Let's plan on 2 centimeter error in the total measurement. If we want that 2 centimeter error to be a 10% error, then we should plan on a 20 centimeter range. We can apply a theoretical formula then to calculate the estimated velocity that we're going to need, and we will find that it's about a half a meter a second. So if we want to get the rolling time to be 1 second, then we want the rolling distance to be a half a meter. Half a meter is about 19.68 inches or 19 and 11/16 inches if your countertop height is 35 inches like mine is. So you can see in the pictures that I've laid a piece of tape out and gotten the tape measure, and we measured 19 and 11/16 from the very corner at the end of the countertop. And we'll measure the time when it crosses the line on the blue tape, and we'll measure the time when it crosses the line, which is the edge of the countertop, as it flies off. Now that we have a velocity measurement set up, we should try it out. And so I rolled a ball, and I attempted to eyeball it as it crossed the start and the stop crossings, and then manually pushing the start and stop buttons on my cell phone timer. I tried this a number of times, and I was unable to start the roll and also keep up with the cell phone. Every time I tried, it seemed like I missed one of the buttons, either the start or the stop, usually the stop. It became clear that if you're going to do this experiment that way, you should have a helper. One person to start the roll and one person to do the start and stop on the cell phone. Now, at my house, you can see my helpers, and Tank's paws are way too big for the cell phone, and Echo thinks that all balls should be taken to the lake and thrown in so that she can go out swimming. So this was not a way that was going to work for me. Videos that look continuous are actually a sequence of pictures that are taken many times a second, and then your brain, when you see them, blurs them together and they look continuous. But in reality, they're a picture followed by a picture followed by a picture, taken at a very regular rate. My cell phone takes videos in MP4 format, which has 30 frames per second, or a picture every 0.033 seconds. So in principle, the video can be used as a stopwatch. If you can view it frame by frame, find the frame where the ball crosses the start line, count frames until you reach the frame where the ball crosses the stop line, and then multiply by the frame time, and you'll have the total roll time of the ball. Provided you can figure out how to view the video one frame at a time. Well, it took me about an hour or so on the web, but it turns out that Windows Media Player allows for viewing with single frame stepping. So I decided to find the frame where the ball is crossing the start line, as you can see below, and then step frames until the ball is crossing the edge of the counter. And in my case, it was 20 frames. And as you can see, the ball's not quite on the edge of the counter, and the next frame it appears to be slightly over. So I would say it was 20 and a half frames, and the time between the tape was 0.677 seconds, and the velocity for this roll was 0.74 meters per second. Now that we have the velocity measurement figured out, let's move on to figuring out how to make the range measurement. That begins by deciding where the origin for the measurement is. The lab procedure says to make a mark on the floor directly below the edge of the countertop. And you can accomplish this by one of two ways. You can hang a weight, perhaps a washer, over from a string, hanging over the edge, so that it almost touches the floor, and then make a mark on the floor. Or you can get a level, and I used a level. I happen to have one that's 6 feet tall, and so I could put it up against the edge, as you see, get the bubble right in the middle. Apparently I can't hold the cell phone straight. And then that made the mark you see on the floor at the end. From there we would measure the range out away from the wall, or away from that line. This procedure for establishing the range measurement origin has a built-in systematic error, and we will discuss that on the next page. The problem with establishing the origin for the range measurement as a line on the floor directly below the edge of the countertop is that when the ball is located directly above the edge of the countertop, it can't fall. And so it hasn't started its free fall, which is essential in the calculation of the range. If the ball is going quite slowly, you can see from the picture that it will have to go one radius of the ball beyond the edge before the back edge of the ball can clear the countertop edge and the ball can begin to fall freely. At higher speeds, the effect isn't so big because of the curvature of the ball. It may launch off far enough that the ball will clear, but without hitting the countertop. But nonetheless, it'll still be a significant fraction of the radius of the ball. So, the range measurement is going to be too long by as much as the radius of the ball. Now, if you use a small ball, as we have, that error becomes quite small, and especially if the radius of the ball is small compared to the range that we're measuring. If you use a large ball, like a tennis ball or a baseball, and you roll it pretty slowly, it can be a very large error in the measurement. Earlier we found that I have great difficulty multitasking. I couldn't start the ball, start the stopwatch, stop the stopwatch. There is no way that I'm going to be able to do all of that and also determine where the ball hit the floor by just simply eyeballing it. And as we've seen, my helpers aren't going to be able to find where the ball hit the floor either. So I need a way to make a mark when the ball hits, and then I can measure to that mark. And as I was thinking about this problem, I was thinking about how long jumpers land in a sand pit, and then they measure from the jumping board to the place where his feet first touch the sand. So I decided to make a ball land in a sand pit, as you can see in the picture. Now the setup is complete and we're ready to try this thing out. When an experiment setup is complete, it should be tested to verify that it works and to assess the accuracy and precision of the method. That is what Table 1 and 2 are about in the lab. There you roll a ball from the same starting point 5 times. You measure its roll time and its range. And then you get the measured velocity to be d over t. And from the range, you can calculate what the velocity should have been. Then you can statistically analyze these two sets of data, meaning you take the average and the standard deviation. The experiment is accurate if the two results are the same, meaning that the error ranges overlap. And the method is precise if the error ranges are small fractions of the averages. Here you see a picture of my first run where the ball hit the sand. It went plop, made a little dimple in the sand and stayed exactly where it hit. Making the measurement was easy. It was 12 1/4 inches. So here are the results from my first trial. The measured time was 0.677 seconds, 20.5 frames on the video. The velocity then that we measured was 0.739 meters per second. The range that we measured was 12 1/4 inches. The velocity is related to the range by the formula shown in the first bullet. At my house, the height was 8.89 meters, 35 inches. So for my countertop, the speed will be equal to 2.35 times the radius. And that will be true for every trial. So keep the number 2.35 and you won't have to keep recalculating the square root every trial. So if we put all that together, we get that the calculated value was 0.74 meters per second. The agreement between the calculated value from the range and the measured value for the, of the velocity is outstanding. The thing is clearly working and is accurate. In order to determine the precision, you have to make a number of runs, and you'll get a range of values. You may get 20 frames and 20 and a half frames and 21 frames. So you get a range of time values and a range of measured velocity values. And you may get 12 inches and 12 and a half inches, 12 and a quarter, 12 and 3/8 inches as you run your various ranges, and you'll get a set of calculated velocities. From those, you calculate averages and standard deviations, and we'll talk about that on the next slide. Now that we have convinced ourselves that the experiment's working properly, it's time to take the data. That means filling in tables 1 and 2 in the lab instructions. And you can build these tables in Excel. If you do that, then Excel can calculate the average and standard deviations for you, and you can format the tables in Excel and then cut and paste them back into your lab report in Microsoft Word. So to do this, you set up columns for each trial and rows for the time, the velocity, the range, and the calculated velocity. And you enter the 5 measured times in the time row. In the first cell of the velocity row, you take the distance and you divide it by the first cell in the time row, and you get the velocity. If you then copy and paste that all the way across the row, it will calculate the velocities of all of the runs. You can calculate the average velocity by taking the cell at the end of the row and typing equal average. Before you get all the way through the word average, a list of functions will show up and you can pick average. And then you can select the row, and as you can see in the picture below, it says average B4 to F4, and it will automatically calculate the average of that row. Then, in the next column to the right, you can start to type equal STD, and by the time you get that far, the list of functions will be up and you can pick standard deviation, which is STDEV. There are many standard deviation options. You want to pick the one that says STDEV. And then again, you select the 5 cells that have the velocity data in it. And you can see it says STDV B4 to F4 in the picture below. And when you hit the return, it will calculate the standard deviation. Once you've done that, you can add the Table 2 data to the bottom of the Table 1 data. So you need to enter the range and then the calculated velocity. I measured the range in inches, so I put in 2 range rows. The first one is the actual measurement, and the next one is the conversion to meters. And then the last row is the calculated velocity in row. You fill in the range measurements across the row that says range in inches. Then you take the first cell in the range in meters and you multiply the cell above it by 0.0254 to get the range in meters. Then you can copy that cell and paste it across the row, and all of the range in meters will fill in. Then in the last row, you use the formula that relates velocity to range. It's that one that has velocity equals the square root of some stuff times range. And remember, we said back on a previous slide, that square root turns out to be a factor of 2.35. So in this case, you just simply take the range in meters and multiply by 2.35. And you use the same technique of calculating the first cell and then copying and pasting across. Then you use the average and standard deviation functions as we did before to get the average calculated range and the average and the standard deviation. In addition, I've added the percent error at the end, which is the standard deviation divided by the average, times 100%. So as you can see, the measured velocities came out to average 0.739 meters per second, and the error was 0.013. The measured ones came out to be 0.735 meters per second, with a standard deviation of 0.006. So those are errors of 1.7% and 0.75%. That's pretty precise for this kind of an experiment. And as you can see, the two average values with their uncertainty ranges do overlap. So there's no reason to believe that there's any systematic error. And these are consistent results when we get the velocity both ways. And that's the purpose of tables 1 and 2. The purpose really is to find out what is the precision of the experiment and is it accurate. And what this data confirms is that it is accurate and it is quite precise. Now we get to what this experiment is really all about. Ultimately, we're conducting it in order to test the theory of projectile motion, which is that the horizontal and vertical motions are independent. That means that the ball is expected to fall to the ground with the same amount of time, which is called the hang time, no matter what the horizontal launch velocity. And we want to test this theory. And we'll do it by making range measurements at various launch speeds and calculating the hang time from the ranges. The analysis that we'll do to get the hang time from the launch velocity and range measurements works as follows. First, we notice that the theoretic relationship that we want to confirm is that the range is equal to the square root of 2 times the height divided by g times the launch velocity. Now this equation describes a straight line if we make a graph of range versus velocity. And the line goes through the origin. And it has a slope that's equal to the value of that square root. And that has the units of time, and it's time times velocity, of course, to get the units of distance, which is the range. It is the hang time. So if we plot our range measurement on the vertical axis and the corresponding velocity measurement on the x-axis, we should find that the points lie on a line. And that line will be given by the equation that the range is equal to alpha times the velocity plus beta. Ideally, since this goes through the origin, beta should be almost 0. Should be equal to 0 theoretically, but of course there will be a little bit of error in our measurements. And alpha should be equal to the hang time, which we know how to calculate because it's just determined by the height of the countertop. To calculate the values of alpha and beta, we will make a graph in Excel and we'll let Excel do all of the work. So you do this by entering your range and launch speed measurements into 2 side-by-side columns in Excel. Enter the speed into the left-hand column and enter the range into the right-hand column. Then we can pick the Insert tab at the top, and then we can select both of the columns as you can see in the blue outline in the picture below. If you pick the scatter plot symbol, the graph will appear. And those are illustrated in the other two pictures. And as you can see, the data points look like they lie on a line. The chart, as it stands right now, doesn't have some features we'd like on it, such as labels on the axis. So what we want to do is change the graph layout. You do that by picking the Chart Tools Design tab, and then near the left you'll see a symbol that says Quick Layout. Pick it, and a bunch of choices will appear. And you can pick one that has labels on the axis. And when you do that, the chart will change and have spots for you to enter those labels. Now what we'd like to do is add a trend line that goes through the data points. And when we do that, we'd like to know what the equation of that line is. And that's how we're going to get the values of alpha and beta. So you'll notice that near the upper right-hand corner of the chart, you will see a plus symbol, which means add elements. Pick it, and a list will appear. Check the box at the place where it says trend line, which is near the bottom of the list. And a trend line will appear on the chart. It's a least squares fit to the data, and I won't go into what all that means, but in some sense it's sort of the line that best fits through all the data points. You can pick the arrow to the right of the trend line and a list of options will appear. And then you can pick more options from the bottom of that list. And you will see the picture to the right. Unfortunately, the snip tool for making screenshots wouldn't allow to show all of those other steps. But in the end, you get to this one, and you check the box that says Display Equation on Chart, which is near the bottom. And when you do that, the equation will appear on the chart, and you will see the next slide. So this is the end result. You can click on the axis titles and replace them. You can click on the chart title and replace them. You can click on the stuff on the right there where it says series, linear series, and delete them, and the chart will get a little bit bigger. And then you can copy this and put it into your Microsoft Word lab report. As you can see, the line goes through the data points. The line has a slope of 0.4043 seconds. And if you run the theoretical calculation, we were expecting that the hang time would be 0.425. So the difference between the theoretical hang time and the one that we get from the experimental data is about 5%. That certainly is within the experimental error. And so we have confirmed that the theory that the horizontal motion and the vertical motion of a projectile moving under the force of gravity are in fact independent. We have concluded the Lab 3 execution, and the only thing that remains is to write the report. One thing that we failed to discuss above is that you should probably also build Table 3 in Excel, much like we did Tables 1 and 2. It simply makes your data analysis easier. And you can copy it into your Microsoft Word lab report. Lab 3 is a formal lab report. You'll find instructions for formal lab reports in the course instructions. It is a report that you type. It is not a report that you get to copy the lab procedure into and then fill in like we do with informal reports. You have to write this one. And you have to begin with a title page, as always, and state the objective, I think by now it should be obvious that the objective here is to test the theory of projectile motion, and then proceed with the data and the data analysis and all of those things that are in the outline for the lab report. The important thing is that you write it and that you submit your own writing. I hope this has been helpful.